Hi, I'm Mindy from Apex Tutoring. Today, we're going to work through the 2022 HSC Mathematics Advanced exam. I'll be assisted by the brand new Casio FX 8200 AU. Let's get started. Okay, question 1. Which of the following could be the graph of y equals minus 2x plus 2? So we have the equation of a line. We'll identify the gradient, which is the coefficient of x. In this case, the gradient is negative 2. And the y-intercept, which is the constant term, of positive 2. Now, the only one of these graphs that has a negative gradient and a positive y-intercept is A. Question 2. Consider the following data set. We have 6 scores, and then it says, which row of the table shows how the median and mean are affected when a score of 5 is added to the data set? Let's first consider the median. The median is the middle score. With 6 scores, the middle is between these two 17s, so the median itself would be 17. Now, if we add a score of 5, it would be the lowest score in the set. So it would go here, and the median would then become the score in the middle, which is this score, which is also 17. So by adding 5 to the data set, the median doesn't change. Now with the mean, 5 is definitely going to be below the mean because it is lower than the rest of the scores. The calculation for the mean includes all of the scores in the dataset. And so unless we're adding a score that is the same as the mean, then by adding a new score to the set, it will change the mean. So the correct answer will be D, which says that the median stays the same while the mean changes. Okay, question 3 says a tower BT has height h meters. From point A, the angle of elevation to the top of the tower is 26 degrees as shown. Which of the following is the correct expression for the length of AB? So this diagram forms a right-angled triangle. For that angle, the tower, TB, which is labeled H, is the opposite side. And AB, which we're being asked for, is the adjacent side. So we can use right-angled trigonometry. If you need to, you can look at the reference sheet. And you'll find the trigonometric ratios here. We're working with the opposite and the adjacent, so we are going to use tan. We can write tan 26 is equal to the opposite, which is H, over the adjacent, which we'll call AB. Now, if we solve for AB, we can multiply AB to the left-hand side and divide tan 26 to the right-hand side. That results in the equation AB is equal to H over tan 26. Now, that's not one of the options, but that's because the reciprocal of tan is cotan. So we can also write this as H times cotangent of 26 degrees. So the answer is B. Question 4. Which of the following is the range of the function f of x equals x squared minus 1? So to find the range of a function, it's very helpful to know what its graph looks like. You may recognize this as a quadratic, which graphs a parabola, and has a vertical translation down 1. So a quick sketch will be useful. Another important feature of this graph is it's an up-facing parabola because x squared is positive. So as you can see, the y values on the graph start at -1 and then go up from there to infinity. Now, it does include -1, and so our range will start with a closed bracket, the square bracket, and then starting at -1 to infinity, and we use round brackets for infinity. So the correct answer is A. All right, question 5. Let h of x equal f of x over g of x, where f of 1 is 2, the derivative of f at 1 is 4, g of 1 is 8, and the derivative of g at 1 is 12. what is the gradient of the tangent to the graph of y equals h of x at x equals 1? So we got to remember that when we want the gradient of the tangent to a graph, we're looking at its derivative. So to take the derivative of h of x, we'll need to use the quotient rule, since it is the quotient of two functions of x. The derivative of h is equal to, if you need a reminder on the quotient rule, remember you can look at the reference sheet. Go to the third page to find derivatives. And the quotient rule is this one here. So we take v times the derivative of u minus u times the derivative of v all over v squared. In this case, it'll be g of x times the derivative of f of x minus f of x times the derivative of g of x all over g of x squared. Now, we're interested in the value of this derivative when x is 1. So that will be g of 1 times the derivative of f at 1 minus f of 1 times the derivative of g at 1 all over g of 1 squared. We have all the information we need, and we're just going to plug it all in. So this will be 8 times 4 minus 2 times 12 over 8 squared. So the answer is D. Question 6. What is the integral of 1 over bracket 2x plus 1 bracket squared? Now, since I could write this integral this way, as 2x plus 1 in a bracket to the negative 2, I can use the power rule and reverse chain rule to do this integral. If you need to remember how to do that, you can look at the reference sheet. So we're going to be looking at this rule here, which is the reversing of the power rule and chain rule. Now, to reverse the chain rule, we'll want to see the derivative of 2x plus 1, which is just 2, multiplied to this function. Since it is not multiplied by 2 currently, what we'll do is we'll multiply this integral by a half and by 2 at the same time. That means we're just multiplying by 1, and we'll be able to use the reverse chain rule for the integral. So that will equal 1/2 times 2x plus 1 to the negative 1 divided by the new power of negative 1 plus c. And when we simplify that, we'll have negative 1 over 2 times 2x plus 1 plus c. So the answer is B. Question 7. Consider the following graph of a probability density function f of x. What is the value of the mode? So when we have a continuous probability distribution, the mode is the highest point on its graph. You could also call this the global maximum of the function. So as you can see, the global maximum occurs here at the point pi over 4, 3 over 2 pi. Keep in mind that the mode is a value, a score, which is x. And so while the peak of the curve is 3 over 2 pi, it occurs at the score of pi over 4. So the answer is C. Question 8. The graph of the even function y equals f of x is shown. The area of the shaded region A is 1/2, and the area of the shaded region B is 3 over 2. What is the value of the integral from negative 2 to 2 of f of x? So we have an even function, which means it's symmetric over the y-axis. We're told that this region here at A is 1/2, and this region here at B is 3 over 2. Now, the integral from negative 2 to 2 would be just double the integral from 0 to 2. It's important to remember that an integral gives us the signed area under a curve, So if some of the area is below the x-axis, it will be negative. And so the integral from 0 to 2 would be 1/2 minus 3 over 2. And we're doubling that since it's even. So that will be 2 times negative 2 over 2, which is equal to negative 2. So the answer is C. Question 9. Liam is playing 2 games. He is equally likely to win each game. The probability that Liam will win at least one of the games is 80%. Which of the following is closest to the probability that Liam will win both games? So, to help us work this one out, we could draw a tree diagram. We can have win or not win, and again, win or not win. So we're told that the probability he will win at least one of the games is 80%. That is these 3 outcomes here, either winning both or one. What that tells us is the probability of losing twice is 20%, as in 100% minus 80%. Since he's equally likely to win each game, he's also equally likely to lose each game. And so that's going to tell us the probability of losing. That the probability of not winning times the probability of not winning again is equal to 20%. So the probability of him not winning is the square root of 0.2. Since we're looking for an approximate answer for a probability, we'll get a decimal. Now that we know the probability of him not winning, we can get the probability of winning. That will be 1 minus our answer. And then to answer the question about the probability of winning both, well, that'll just be the square of this answer. And the closest is A at 31%. Question 10. It's last multiple choice question, and it's usually the hardest. So the graphs of y equals f of x and y equals g of x are shown. Which graph best represents y equals g of f of x? So here are our options. And let's take a look back at the original 2 functions. Well, I won't need the calculator for this one, so I might give it some extra working out space. To figure out which is the graph of the composition of these functions, we need to consider how a composition works. So as we progress through values of x, they will first be put into f of x. Then the outputs of f of x become inputs for g of x. So we might drop a table of values to help us consider different values of x and what happens to the composition. Now we don't have specific values that we can plug in, but we can see on f of x, the inner function, that the domain includes negatives, 0, and positives, and there don't seem to be any domain issues. So let's say that we're plugging in something like -2, -1, 0, 1, and 2, and let's consider what happens. Now, before we go doing that, I'd like to point out that there will be a domain issue on g of x. G of x seems to have a vertical asymptote at a positive number. So if f of x climbs through positive numbers, whether it's going up or it's going down, then it will cross over this point where the outer function g of x has a vertical asymptote. So we'll be on the lookout for that as we test some values out. So let's start with -2. And if we plug it in first, the inner function f of x, about what would that look like? So the output on f of x around, say, -2 would be a large-ish positive number. Let's pretend that's something like 4. Then if we plugged in -1, then f of x will be positive still, but smaller. So let's say maybe that's 1. Then as we progress through further on values of x, we might get to something like 0. And on f of x, its output would be 0. Then if we continue to the right, f of x appears relatively symmetric. So if we plugged in a symmetric positive number like +1, we will get a similarly positive small value like +1. And then plugging in +2, we will get something similar to what happened when we would plug in something like -2, and we might get something like 4. Now, let's look at the composition g of f of x, remembering now that the outputs of f of x are now inputs for g of x. So we can see the outputs for f of x start high positive, go down to 0, and then go back to high positive numbers. So what happens to g of x as we do that? So if we start then with x being -2, f of x is then 4. So we're starting off somewhere maybe over here. And g of x will be a smallish positive number. So maybe it's something like 1/2. Then, if x were -1, f of x would be a smaller positive number. So we're actually traveling now towards the left along the graph of g of x. So maybe we're somewhere over here at around, say, 1. And g of x would be a slightly larger positive number. Let's say maybe it's around 1. Then as we progress through x values from -1 to 0, f of x is going to regress from 1 to 0. So as you can see, it's going to cross over its asymptotes, right? And so somewhere in here, we're going to have a vertical asymptote. Just before we cross that asymptote, the values of g of x get very large and go to infinity. And then we'll cross to the other side, and the values of g of x will be very large towards -infinity. And then when we get to 0, well, g of x looks like it will be 0. Now, as we continue through values of x, the inner function f of x goes back up through the positive numbers. So then it's going to be traveling right along the graph of g of x. So once again, we're going to cross that vertical asymptote, first going very large negative, and then very large positive. We'll get back to 1 again, and we guessed g of x would be something positive, small-ish, but maybe like a 1, and then we would get to 2 again, and g of x would be a little bit smaller actually, something like 1/2. So now let's look at our options and see if we can find a graph that matches this behavior. Okay, so we're looking for a graph that as x goes to -infinity, the graph seems to be getting smaller. At 1, it's around something like 1, positive. And then it will be slightly increasing, and then it will just go up to positive infinity along a vertical asymptote. Then after that asymptote, it's going to be at -infinity, and then at 0, it'll be at 0. Then the behavior repeats, and it's going to go back down to -infinity. It'll have a vertical asymptote, and then up at positive infinity, going down to 1, and then decreasing as x goes to infinity. So the graph that actually best matches that behavior would be B. As you can see, at 0, it's 0, and it has those two vertical asymptotes symmetrically. It has that infinity behavior that we discussed, as well as decreasing towards possibly 0 as x goes to negative and positive infinity. So B would be the best answer for this one. All right, question 11. The table shows the types of customer complaints received by an online business in a month. What are the values of A and B? So in our table, we have frequency, and cumulative percentage. Now, A is the cumulative frequency of delivery fee. Remember, with cumulative frequency, we are just adding up the running total as we go. So the first one starts at 98, and then in the second row, we'll add the 62 to get A. So A is 180. Now B is the cumulative percentage of damaged item. So we just need to find out what 192 is as a percentage of the total, which, as we can see, is 200. They're writing that column as a whole number, so we'll just multiply by 100, which is 96. Part B says, the data from the table are shown in the following Pareto charts. The manager will address 80% of the complaints. Which types of complaints will the manager address? So remember, with the Pareto charts, the line graph shows us the cumulative percentage, which follows the vertical axis on the right. We're looking for cumulatively 80%. So we can see that occurs at delivery fee. Remember, that includes that outcome and everything before it. And so if stock shortage and delivery fee are addressed, cumulatively that will be 80% of the complaints. Question 12. A student believes that the time it takes for an ice cube to melt, m minutes, varies inversely with the room temperature, T degrees Celsius. The student observes that at a room temperature of 15 degrees Celsius, it takes 12 minutes for an ice cube to melt. Find the equation relating m and t. So we're going to fit this to an inverse variation model, which is of the form y equals k over x. In this case, our dependent variable is minutes to melt. K is our constant of variation, and our independent variable is temperature T. Now we can use the given information to find K, the constant of variation. We're given it takes 12 minutes when the temperature is 15, and we can solve for K. Multiply both sides by 15. K is 180. Let's write the completed model. M equals 180 divided by T. Part B, by first completing this table of values, graph the relationship between temperature and time from T equals 5 degrees to T equals 30 degrees Celsius. So we'll use M equals 180 over T to complete the table of values and graph the curve. When T equals 5, M will equal 180 divided by 5, which is 36. When T equals 15, that's what was given above, M equaled 12, but we can also calculate it. And when T equals 30, M will equal 180 divided by 30, which is 6. Now we'll plot those points. We have 5, 36, 15, 12, and 30, 6. This is an inverse variation graph, also known as a hyperbola. So the graph will look like this. Question 13. Use two applications of the trapezoidal rule to find an approximate value of the integral from 0 to 2 of the square root of 1 plus x squared. Give your answer correct to 2 decimal places. So, the trapezoidal rule is on the reference sheet. You'll find it at the bottom of the integral section. Here we have the integral is approximately equal to b minus a over 2n times f of a plus f of b plus 2 times f of all the values in between a and b. So when doing trapezoidal rule, I usually like to do a quick sketch. Usually you don't even need to know what the graph looks like. We're approximating the area from 0 to 2 with two applications of the trapezoidal rule. So that tells us that the middle value is 1, and there's two trapezia or two sections here that we're going to be using to approximate the area. So n equals 2. So the integral will be approximately equal to b minus a is 2 minus 0 over 2 times n, so 2 times 2, times f of a, which is f of 0, plus f of b, which is f of 2, plus 2 times f of the middle values, which in this case is just 1, which is f of 1. Now, f of x is the function in the integral. So f of 0 will be the square root of 1 plus 0 squared. F of 2 is the square root of 1 plus 2 squared. And f of 1 is the square root of 1 plus 1 squared. We want an approximation to 2 decimal places, so let's work this out. So we get 3.03 to 2 decimal places. Question 14. The graph of y equals k sine of ax is shown. What are the values of k and a? Now, k and a are related to transformations of the graph. Specifically, they are dilations. It can also be helpful to remember the standard form for a sine or cosine graph. Something like y equals k sine ax plus b plus c. K is the vertical dilation in the context of sine or cosine. It's also going to be the amplitude of the graph. Normally, sine goes between -1 and 1. This graph goes between -4 and 4. The amplitude is 4. The vertical dilation is 4. And so K is equal to 4. A is horizontal dilation. In the context of sine and cosine, it's also related to the period of the graph. In fact, the period of the graph is the usual period of sine or cosine or tangent, which in this case for sine is 2 pi, divided by the coefficient of x, which is a. Now let's identify the period of this graph. Normally, I might look at how long it takes to repeat. So for example, from here to here, which appears to be 6 pi. So the period of this graph is 6 pi. We can solve for a. So a is 1/3. Question 15. In a bag, there are 3 six-sided dice. 2 of the dice have faces marked 1 through 6. The other is a special die with faces marked 1, 2, 3, 5, 5, 5. One die is selected and tossed. What is the probability that the die shows a 5? So we could use the product rule here, but if it helps, you could draw a tree diagram. There's 2 kinds of dies. One is a standard die. The other is non-standard. We're simply interested in the probability of throwing a 5. So we don't have to put all outcomes here. We can just write 5 or not 5. Now 2 out of 3 are standard dice. 1 is non-standard. On a standard die, of course, rolling a 5 is 1 in 6. And on the non-standard die, the probability of rolling a 5 is a half, or 3/6. So the 2 ways to get a 5 are 2/3 times 1/6 and 1/3 times 1/2. So the probability is 5 out of 18. Part B says, given that the die shows a 5, what is the probability that it is the special die? So this is a conditional probability question. We can get a formula for conditional probability from the formula sheet. On the second page, this formula here is for conditional probability. The probability of A given B is the probability of A and B divided by the probability of B. So the probability that it's the special die, which I called non-standard, given it's a 5, is the probability of it being non-standard and it's a 5 divided by the probability that it's a 5, which we happened to work out in part A. So what's the chances of it being non-standard and a 5? Well, that is just 1/3 times 1/2. And the probability of 5, as we worked out, is 5 out of 18. So the answer is 3/5. Question 16. The parabola y equals x squared meets the line y equals 2x plus 3 at the points -1, 1 and 3, 9, as shown in the diagram. Find the area enclosed by the parabola and the line. So we're finding the area between 2 curves, and we're going to use an integral. We already know the points of intersection, so we already know the limits of integration. We'll be integrating from -1 to 3, which are the x-coordinates of the intersections, of the top function, which is the line, 2x plus 3, minus the bottom function, which is the parabola, which is x squared. So we just need to work that out. Sometimes we'd like to simplify the expression inside the integral. In this case, there's not really anything to simplify. So the integral will be 2x squared over 2 plus 3x minus x cubed over 3. And we'll be plugging in from -1 to 3. Now, on that first term, the 2's do cancel. So when I plug in, I will get 3 squared plus 3 times 3 minus 3 cubed over 3 minus, plugging in -1, -1 squared plus 3 times -1 minus -1 cubed over 3. So this will be so that would be 10 2/3 or 32 over 3. Question 17. Cards are stacked to build a house of cards. A house of cards with 3 rows is shown. A house of cards requires 3 cards in the top row, 6 in the next row, and each successive row has 3 more cards than the previous row. Show that a house of cards with 12 rows has a total of 234 cards. So, we need to recognize that this is an arithmetic series. And it's arithmetic because each next row is just 3 more than the last. So we're adding a constant amount of 3 to each next term. And the question in part A is asking us for a total, so the sum of 12 terms of this series. The formulas for arithmetic and geometric sequences and series are on the formula sheet. On the first page, we have these formulas for the sum of n terms of an arithmetic sequence. We'll be using the first version since we don't have the first and last terms. So that equals n over 2, in this case 12 over 2. 2 times a, the first term here is 3, plus n minus 1, times d, the common difference, in this case 3, since we're adding 3 to each row. And we get 234 as expected. Now part B, another house of cards has 828 cards. How many rows are in this house of cards? So now we know Sn, and we're asked to find n. So we'll write n over 2, 2 times a, which is still 3, plus n minus 1 times the common difference, again, which is 3. And we'll solve for n. First, so I don't have any pesky fractions, I might times both sides by 2. And I'll expand it in a bracket. And then simplify it a little bit. Now I'll expand this bracket. And it's quadratic. So let's get everything to one side. Let's divide everything by 3 to simplify things a little bit. We're looking for 2 numbers that multiply to negative 552 and add to 1. 552 divides by 24. So that's 24 and 23, which are 1 apart. If we want it to be negative, we'll put the negative on 24. So this is n minus 24 times n plus 23 equals 0. So technically, n could be 24 or negative 23, but we wouldn't have negative terms in a geometric series. So we'll go with n equals 24. Question 18. Part A, differentiate y equals bracket x squared plus 1 bracket to the power of 4. So it's just a differentiation question to start with. We're going to use the power rule and the chain rule. Now, if you do need a reminder, you can find some of this on the formula sheet. The third page with derivatives. You have the power rule here, and you have the chain rule as well. So the derivative here is 4 times the inner function unchanged to the power of 3. That's the power rule. Now for the chain rule, we multiply by the derivative of the inside, which is 2x. We can simplify that a little bit. That'll be 8x times the bracket to the power of 3. Now part B, we have hence or otherwise find the integral of x times the bracket x squared plus 1 bracket to the power of 3. So we'll use the result in part A. The only difference between what's inside the integral and what we got in part A is that factor of 8. And that's easy to fix. So we can always get a missing constant factor by both multiplying by the factor and the reciprocal of that factor at the same time. I usually write the factor that we want inside the integral and the one that we don't on the outside. As you can see, this would simplify back to this original integral, so we haven't really changed anything. Now we know the integral of that stuff inside the integral is what we started with in part A, and we just have the factor of 1/8 in front of that. Don't forget to put plus c. And that's our answer. Question 19. The graph of the function f of x equals x squared is translated m units to the right, dilated vertically by a scale factor of k, and then translated 5 units down. The equation of the transformed function is g of x equals 3x squared minus 12x plus 7. Find the values of m and k. So in order to identify the transformations on x squared, we'll have to use completing the square to turn this into what we sometimes call vertex form of this quadratic. First, we're going to factorize the 3 from the first 2 terms. Then we'll complete the square on the quadratic inside the bracket. Remember to take half of the coefficient of x and square it, and both add it and subtract it to that quadratic. So half of 4 is 2, and 2 squared is 4. We'll add 4 and subtract 4, which technically means we're adding 0. Now, when completing the square on non-monics, we want to take out that term that's not going to be part of the perfect square, but we'll have to multiply it by the factor in front of the bracket as we pull it out. So when I pull out that minus 4, it'll be multiplied by 3 and become minus 12 outside the bracket. Now this will simplify and factorize. Now that we've done that, we can clearly identify the transformations that happened to x squared. So we have a vertical dilation of a factor of 3, and that's going to be k. We also have a horizontal translation of 2 to the right. Remember, horizontal transformations are always opposites. So m equals 2. And that's everything we need to do. Question 20. A scientist is studying the growth of bacteria. The scientist models the number of bacteria, n, by the equation n of t equals 200 times e to the power of 0.013t, where t is the number of hours after starting the experiment. Part A, what is the initial number of bacteria in the experiment? Now, if you're well familiar with exponential models, you probably can identify this right away as being 200, the number in front of the exponential. However, the initial number will occur when t is 0. We could plug that in to work it out if we needed to. The reason the 200 is the initial amount in the exponential is because anything to the power of 0 equals 1. So initially there are 200 bacteria. Part B, what is the number of bacteria 24 hours after starting the experiment? So now we just want to make t 24. So we'll calculate that. And round to the nearest whole number, 273. Part C, what is the rate of increase in the number of bacteria 24 hours after starting the experiment? Anytime we're asked for a rate, we are looking at the derivative. So, the derivative of n of t is 200 times. Now, when differentiating an exponential, you can look at the reference sheet if you need a little reminder. This here tells us that the derivative of e to the f of x is e to the f of x times the derivative of f of x, bit of a chain rule. So the derivative of that function in exponential, 0.013t, is just 0.013. And then the derivative of e to the 0.013 itself is e to the 0.013. Now we want to know what's the rate when t is 24. We'll plug that in. And that is 3.55 bacteria per hour. Question 21. Eli is choosing between two investment options. Option 1, depositing a single amount of $40,000 today, earning interest of 1.2% per annum compounded monthly. Option 2, depositing $1,000 at the end of each quarter, earning interest of 2.4% per annum compounded quarterly. And we have a table of future value interest factors for an annuity of $1. Part A is, what is the value of Eli's investment after 10 years using option 1? So notice that option 1 is a lump sum investment, which means it's regular compound interest. The compound interest formula is on the reference sheet if you need it. That's this one here. So the amount in the account at the end, which is also sometimes called the future value, is the principal, 40,000, times 1 plus R. Now here, R is monthly, 1.2% per annum is equivalent to 0.1% per month, or in the formula, we could put it over 12. And if it's monthly for 10 years, 12 times 10, 120. So it will be $45,097.17. Part B, what is the difference between the future values after 10 years using option 1 and option 2? So option 2 is an annuity, and we know that because we're depositing $1,000 at the end of each quarter. So it's not a lump sum investment, it's regular deposits over a period of time. And we'll use the table to work out the annuity, and we won't need to use a sequence to work it out. So when using a table, the future value is equal to the contribution per period, which we often use A, times the number in the table. So in this case, the contribution is 1,000. Let's find the number in the table. It's 2.4% per annum, but it is compounded quarterly. So the interest rate is 2.4% divided by 4, since there's 4 quarters in a year. That's 0.6%, or as a decimal, 0.006, and the number of periods is 4 quarters per year for 10 years, which is 40. So this is our number in the table to multiply by. That'll equal $45,056.30. So the difference would be $40.87. Question 22. Find the global maximum and minimum values of y equals x cubed minus 6x squared plus 8, where x is between and including -1 and 7. Okay, to find global max and min, we need to find all stationary points in the domain, check their heights, as well as check the height of the function at the endpoints. So I'll have a quick sketch just to visually keep track of what we find. Now, let's check the endpoints first so we don't forget. At -1, y will equal 1. At 7, y will equal 57. Not scale. Now let's find any stationary points so we can find local maxes and mins. The derivative is 3x squared minus 12x, and stationary points occur when the derivative is 0. To solve, let's factorize. And so we have stationary points at 0 and 4. So we don't necessarily even need to know the nature because we're just trying to find out what's the highest point and what's the lowest point. So let's just substitute those back into y. At 0, y would equal 8. At 4, y would equal -24. So the graph will essentially look something like this. Really, though, we're just interested in what's the maximum value of y and what's the minimum value of y. In this case, the global maximum is not actually a stationary point because at the end of the domain, the function is higher than the local maximum, which occurred at x equals 0. So the maximum value is 57. The minimum value does occur at a local minimum because that's the lowest point on the graph on this domain. So the minimum value is -24. Question 23. The depth of water in a bay rises and falls with the tide. On a particular day, the depth of the water, d meters, can be modeled by the equation d equals 1.3 minus 0.6 cosine of 4 pi over 25 times t, where t is the time in hours since low tide. Part A, find the depth of water at low tide and at high tide. So let's think about this cosine function and the transformations. Normally, cosine starts at 1 and then cycles every 2 pi, and its minimum value in the middle is -1. If we look at this cosine function, we can see there is a vertical reflection and a vertical dilation factor 0.6. So this cosine graph will be upside down and we'll be having a min and a max of 0.6 and -0.6. Another important feature here is the vertical translation. This graph has been shifted up by 1.3. So if we add 1.3 to the max and min values, we'll have the new graph as well as the low and high tide values. So the low tide will be 1.3 minus 0.6, so 0.7 meters, and the high tide will be 1.3 plus 0.6, so 1.9 meters. Part B. What is the time interval in hours between two successive low tides? So now we need to consider the period of the cosine graph. As we said earlier, the period is normally 2 pi. However, if the independent variable, the variable inside of the cosine or other trig function, has a coefficient, that is a horizontal dilation and affects the period. So we see the coefficient of t here is 4 pi over 25. To get the period of any trig function, take its usual period. So for sine and cosine, that's 2 pi. For tan, it is 1 pi. And then divide by the coefficient on that independent variable. So we'll be dividing by 4 pi over 25. So that's 12.5 hours. Since the period is 12.5 hours, that will be the length of time between any two successive low tides. I'll also adjust our graph to show that period. Part C. For how long between successive low tides will the depth of the water be at least 1 meter? So we're going to try to find when the height of the function is at 1. So that will be around here. We're looking for these two times because for the time in between, the tide will be above the 1 meter level. So to find those times, let's set the function equal to 1 and solve for t. First, we might subtract 1.3. Then divide by negative 0.6. So we get 1/2 equals cosine of 4 pi over 25t. Next, we're going to find the angles for which cosine equals 1/2. That's going to be an exact value, so I'll look at the reference sheet at our right angle triangles. As you can see, cosine 60 is 1/2. We're working in radians, and that's always the case for when we're doing applications that don't involve angles. So 60 degrees is pi over 3. That tells us that what's inside cosine has to equal pi over 3. That's just the first time that it will equal pi over 3 in the first quadrants. Remember, cosine is also positive in quadrant 4, and that'll be the next time. Now that angle is 2 pi minus pi over 3, so 5 pi over 3. Now get t, we just have to divide both of these answers by 4 pi over 25. So t will equal 25 over 12 and 125 over 12. Remember, we're looking for the time interval between these two times, so we'll subtract. And we'll find out what that equals. 8.3 repeating hours. So we could say that that is 8 1/3 hours, or 8 hours and 20 minutes, since 1/3 of an hour is 20 minutes. Remember, if you ever do need to convert from decimal hours into hours and minutes, you can use the degrees, minutes, and seconds button on the calculator. And that confirms 8 hours and 20 minutes. Question 24. Joe is researching the relationship between the ages of teenage characters in television series and the ages of actors playing these characters. After collecting the data, Joe finds that the correlation coefficient is 0.4564. A scatter plot showing the data is drawn. The line of best fit with equation y equals negative 7.51 plus 1.85x is also drawn. Describe and interpret the data and other information provided with reference to the context given. This is a 4-mark question, so we need to make sure to identify 4 features of the data. Let's start with the correlation coefficient. 0.4564 indicates that the correlation is relatively weak. It's also positive, so we can write that and say the relationship is weak and positive since the correlation coefficient is 0.4564. Let's add some meaning to that statement. We can explain that this means that the higher the age of the character, the higher the age of the actor tended to be. Another thing we can reference is the information in the line of best fit. Now, in this case, the y-intercept does not have a lot of meaning. That's partly because the y-intercept occurs when x is 0, and that is extrapolation. That is far outside the range of the data we collected. It also doesn't make sense to have a negative age. However, in lines of best fit, the gradient is pretty much always relevant unless the correlation does not exist. So what that gradient tells us is how much more you have of y for every 1 unit increase in x. Let's put that into this context. So, for every 1 additional year in age of the character, which is on our horizontal axis, our independent variable, the age of the actor was 1.85 years older on average. The last thing we can point out about this relationship is the validity of it. For what ages can we use this model to predict ages of actors? So as you can see, the data we collected was only for ages of characters from 14 to 17. So our model is only valid for ages of characters 14 to 17 years old. We'll write the model is valid for ages of characters 14 to 17. Since that is the range of data collected. That should be enough for our 4 marks. We have touched on 4 things: that the relationship is weak, positive, what that means, as well as what the gradient tells us about the increase in age of the actor for every 1 additional year of age of the character, and lastly, as well, the validity of the model. Question 25. Let f of x equal sine 2x. Find the value of x for x between 0 and pi, for which the derivative of f of x equals negative root 3, and the second derivative of f of x equals 2. So let's start with the derivative of f of x. If you need to, you can look at the reference sheet to remember the derivative of sine, as well as the chain rule that applies. On the page with the derivatives, we see the derivative of sine is cosine, and it even shows us how the chain rule applies, and the chain rule, if we need it, is here. So, the derivative of sine is cosine times the derivative of the inner function. The derivative of 2x is 2. So it's going to be 2 times cosine of 2x. We're looking for when this is equal to negative root 3. Let's solve for cosine by dividing by 2. That will be an exact value, so let's go look at our two right triangles. Cosine is root 3 over 2 at 30 degrees. We'll call that our reference angle because this is equal to negative root 3 over 2, so it's not going to be in quadrant 1. We're also working in radians, and 30 degrees is pi over 6. Now, cosine's negative in quadrants 2 and 3, so we'll need that angle in those quadrants. So that will be pi minus pi over 6, which is 5 pi over 6, and pi plus pi over 6, which is 7 pi over 6. Now, we should consider the domain that we were given from 0 to pi. Since it's not just cosine of x and it's cosine of 2x, we can make an adjustment on that domain by multiplying through by 2. That would be 0, 2x, 2 pi. As in, if x is between 0 and pi, then 2x can be between 0 and 2 pi. So we've found all the values for which cosine 2x equals negative root 3 over 2 between 0 and 2 pi. Now let's look at that second derivative. Remember that first derivative was 2 cosine 2x. Now, the derivative of cosine is sine. Don't forget to multiply by the derivative of the inner function as the chain rule. So the derivative of 2x once again is 2. When we multiply this function by 2, it'll become 4 sine 2x, and don't forget the negative. And we're looking for when the second derivative equals 2. And for the value that coincides with one of the two angles we have already found. 5 pi over 6 or 7 pi over 6. Now let's solve for sine by dividing by negative 4. So we're looking for when sine 2x equals negative 1/2. Looking back at our triangles, we can see that sine will equal 1/2, again, at 30 degrees. So our reference angle, once again, is 30 degrees or pi on 6. However, we're looking for when sine is negative. Now sine is negative in quadrants 3 and 4. So we'd be looking at 7 pi over 6 again, or 2 pi minus pi over 6, 11 pi over 6. Of course, the one we want is the one it has in common with the first derivative being negative root 3 over 2, so that will be 7 pi over 6. Now we know that we're looking for when 2x is equal to 7 pi over 6. We just need to finish solving for x by dividing by 2. So we get 7 pi over 12. Question 26. The lifespan of batteries from a particular factory is normally distributed with a mean of 840 hours and a standard deviation of 80 hours. It is known from statistical tables that for this distribution, approximately 60% of the batteries have a lifespan of less than 860 hours. What is the approximate percentage of batteries with a lifespan between 820 and 920 hours? So it can be helpful to draw up a normal distribution. Our mean is 840. The standard deviation is 80. So we can add and subtract lots of 80 to fill in the standard z-scores. Now the question says that from statistical tables we know 60% of batteries have a lifespan of less than 860. So if I put that on here, 860 will be around here. And we know that this down here is 60%. Now the question is asking us for the percentage between 820 and 920. So that would be here to here. Now, we don't quite have information about the percentages below or above 820. However, notice that 820 is symmetrically below the mean compared to what we were given at 860. 860 is 20 above, and 820 is 20 below. Now we know that 60% of the data will be below 860. That means that 40% will be above. Symmetrically, that means that 40% will be below 820. Now, as for 920, that's easy because that's on our reference sheets, since that it has a z-score of 1. So we can see that 68% of scores are between -1 and 1, which leaves 32% outside in the tails. Symmetrically, that means the top tail is 16%, which means that above 920 is 16%. So between 820 and 920 is 100%, minus 40%, and minus 16%. 44%. Question 27. Let f of x equal x times e to the negative 2x. It is given that the derivative is equal to e to the negative 2x minus 2x times e to the negative 2x. Show that the second derivative is equal to 4 times x minus 1 in the bracket times e to the negative 2x. So I recommend taking that first derivative and first factorizing it to make the second derivative a little easier for us. We can factorize out e to the negative 2x. That just means we have a simple product rule to work out here. Now, if you need a reminder, the product rule is on the formula sheets. The product rule is u times the derivative of v plus v times the derivative of u. So if we take the second derivative, we'll have e to the minus 2x, which we might treat as u, times the derivative of the second function, which is in the bracket, which will be negative 2, plus, now we'll have the second function, 1 minus 2x, times the derivative of the first one, which is negative 2 times e to the negative 2x. Remember, if you need to look at the reference sheet, you can find how to do the derivative of an exponential. Now let's simplify a little bit. And lastly, we can factorize and just change the order of the addition. They've factorized the 4 onto the left of the bracket and the e to the minus 2x onto the right of the bracket. And we have the results. Part B, find any stationary points of f of x and determine their nature. So stationary points occur when the first derivative is 0. For our convenience, let's use the factorized version. Because similarly to a quadratic, when something is factorized and equal to 0, we can solve it by finding what makes each factor equal to 0. Now, e to the x never equals 0. We know that by considering exponential functions and their horizontal asymptote, as well as the fact that when you take a positive number to a power, it will never be 0 or negative. So that factor contributes no solutions. The only solutions will come from the bracket, and that bracket equals 0 when x equals a half. Now, if we want a point, we will also want the y-coordinate that goes with this x-coordinate. So, when x is a half, y will equal 1/2 e to the negative 2 times a half, which notice how I'm using the original function to get. Now, to determine the nature, we might as well use the second derivative since we already have that. We want to know what's the sign of the second derivative at x equals 1/2. Now we have a positive number times a negative number, since 1 minus a half would be negative, and e to any power is a positive. A positive times a positive is negative. So the answer is negative. But you can also work out the value and see if that comes out positive or negative. So since the second derivative is negative at that stationary point, it means our function is concave down at that point, and we have a local maximum. Now part C, sketch the curve of y equals x to the negative 2x, showing any stationary points, points of inflection, and intercepts with the axes. So the things we haven't found yet are points of inflection and the intercepts. Now, points of inflection occur when the second derivative is 0 and changes sign on each side. The second derivative was for x minus 1 e to the negative 2x. When will that equal 0? Well, once again, an exponential with a positive base could never equal 0 or negative. So the only factor contributing solutions here is the bracket, where when x equals 1, it will be 0. It's good practice to check the sign of this function on each side to make sure that it's changing concavity. So to the left of 1, we might try substituting 0. When x is 0, we'll have 4 times negative 1 times e to the 0, which is negative. To the right of 1, we could try 2. In that case, we'll have 4 times positive 1 times e to the negative 4, which will come out positive. So we know it's concave down, and then we have an inflection point, and then it's concave up. Now, noting that we already tested x equals a half earlier and found that second derivative to be negative, we might have already known, but plugging in 0 was also pretty easy to do. We'll also need those intercepts of the function. So, y-intercepts occur when x is 0. When x is 0, y will be 0 times e to the 0, which is 0. That means we have a y-intercept of 0. To find x-intercepts, we make y 0. When y is 0, we have 0 equals x times e to the minus 2x. As we discussed, the exponential cannot be 0 or negative. So the only way for this product to be 0 is for x to be 0. And we already have that intercept as part of the y-intercept. So the only intercept is through the origin. Now we can sketch the graph. Our graph goes through the origin. We have a stationary point at 1/2 1/2 e to the negative 1. That's a positive value. If you wanted to get an approximate number, you could work that out in the calculator. It's a local maximum. We have an inflection point when x is 1. For the y coordinate, we could plug that into y. So that should come out a lot smaller than e to the negative 1. So it'll be around here. And we know the graph is concave down to the left of 1. And is concave up to the right of 1, but has no x-intercepts and no more stationary points. So it'll probably look something like this. So that's our graph. Question 28. The graph of the circle x squared plus y squared equals 2 is shown. The interval connecting the origin and the point 1, 1 makes an angle theta with the positive x-axis. Part A, by considering the value of theta, find the exact area of the shaded region as shown on the diagram. So we have a right triangle where the two legs are both 1, which means it's an isosceles right triangle, and theta must be 45 degrees, or in radians, plan 4. Okay, to find the shaded area, we'll consider the sector, and if we subtract the area of this triangle here, we will get the shaded area over here. So the area of a sector, if we're using radians, is on our formula sheet in the trigonometry section here. If you use degrees, you can use the other formula, which happens to be up here. So we have the area is 1/2 r squared theta, if theta is in radians. The radius of the circle is the square root of 2. Remember that for the equation of a circle, x squared plus y squared equals r squared. And if 2 is r squared, r is the square root of 2. We can also get that by using Pythagoras on this right triangle. Again, theta is pi over 4. We're looking for exact area. And in this case, it comes out to pi over 4. Now we want the area of the triangle. The base and height are 1. So the area, being 1/2 base times height, equals 1/2. That means the shaded area is the area of the sector, pi over 4, minus the area of the triangle, 1/2. And we'll leave it like that since we want exact area. Now we have part of a hyperbola y equals a over b minus x minus 1, which passes through the points 0, 0, and 1, 1, is drawn on the circle x squared plus y squared equals 2 as shown. And for part B, we need to show that a equals b equals 2. So to find a and b, we can use the 2 points that the hyperbola passes through to solve for them. It passes through 0, 0. So that means 0 equals a over b minus 0 minus 1, which means that a over b equals 1, which means a equals b. Now with 1, 1, we have 1 equals a over b minus 1 minus 1. Since a is equal to b, we can replace one with the other, so we could write something like 1 equals a over a minus 1 minus 1, and solve for a. I'll add the 1 to both sides. Multiply both sides by a minus 1. So subtract a from both sides, and add 2 to both sides. A equals 2, and since a and b are equal to each other that we found here, b also equals 2. Now part C, using parts A and B, find the exact area of the region bounded by the hyperbola, the positive x-axis, and the circle as shown on the diagram. So if we're thinking area under a curve and integrals, we'll notice that the area here can be divided into 2 regions. The first region is here under the hyperbola, and the second region we actually already found. So let's find that area under the hyperbola using an integral. We'll be integrating from 0 to 1 of 2 over 2 minus x minus 1 dx. Now that first part of this function, we'll need to use a logarithm to integrate. Now the derivative of the denominator is -1, so we might make a slight adjustment here. We can put the numerator factor 2 in front. We want a -1 in the numerator, so we'll also times in front by -1, which will technically cancel itself out. And now it's in the form that we'd like. Of course, the constant does not need to be adjusted. So if we integrate that, we'll have the -2 factor in front, and then we'll have ln of the absolute value of 2 minus x. And then, of course, the integral of -1 is just minus x. And we're going from 0 to 1. So if we plug in 1, we'll get -2 ln 1 minus 1. And if we plug in 0, we'll get -2 ln 2 minus 0. Now, ln of 1 is equal to 0, so we're going to get -1 plus 2 ln 2. Now, don't forget we need to add on that extra bit of the area, this part over here that we found in part A, which was pi over 4 minus 1/2. If we simplify a little bit, we'll have 2 ln 2 plus pi over 4 minus 3 over 2. This can also be written using log laws as ln 4 plus pi over 4 minus 3 over 2. And if you like, you could put this all into one fraction. Question 29. The diagram shows the graph of y equals 2 to the minus x. Also shown on the diagram are the first 5 of an infinite number of rectangular strips of width 1 unit and height y equals 2 minus x for non-negative integer values of x. For example, the second rectangle has a width 1 and a height of 1/2. That's this one here. The sum of the areas of the rectangles forms a geometric series. Show that the limiting sum of this series is 2. So let's start writing down the areas. The area of the first rectangle is 1 times 2 to the -0, which equals 1, so that's just 1. The second has a width of 1 and a height of 2 to the -1, which is 1/2, so the area is 1 over 2. The next one, with 1, height 2 to the -2, which is 1/4. And then we have with 1 and height 2 to the -3, or 1/8. And the fifth one is 1 by 2 to the -4, 1/16. We can see that geometric series where the first term is 1, r is 1/2, each term is 1/2 times the previous term, and it will have a limiting sum since the absolute value of r is less than 1. Now, The information in the formula for the limiting sum is on the reference sheets. So here you can see the formula and the condition that the absolute value of r must be less than 1. So the limiting sum will be a over 1 minus r, which is 1 over 1 minus 1/2, which is equal to 1 over 1/2, which is equal to 2. Part B, show that the integral from 0 to 4 of 2 to the negative x is equal to 15 over 16 ln 2. So to integrate an exponential like this, we can check the reference sheet. So we can see here how to do the integral of an exponential along with reversing the chain rule. So that's going to equal a to the f of x over ln a. We just have to make sure that the derivative of the inner function is multiplied by our exponential. So here, the derivative of negative x would be negative 1. We are missing that negative, but it's easy to add that in. So essentially multiplying by negative 1 twice. We can rewrite this integral without changing it. So that will equal negative, which is in front of the integral. Then we have 2 to the negative x over ln 2. And we're going from 0 to 4. Now substituting in 4, we'll have 2 to the negative 4 over ln 2. And substituting in 0, we'll have 2 to the 0 over ln 2, which will equal negative 1 over 16 ln 2 minus 1 over ln 2. We can combine these fractions. And we get the result. Part C, use parts A and B to show that e to the 15 is less than 2 to the power of 32. So this question is all about area, and we want to use these two results in an inequality. So if we look at the diagram, we can see that the sum of the areas of the rectangles will be less than the area under the curve because of the way those rectangles are set up, such that their left-hand side is at that height of that decreasing function. So we know that the sum of the areas of the rectangles will always be greater than any area under that curve. We can say that the area under the curve that we found in part B, which was 15 over 16 ln 2, would have to be less than the sum of the areas of all the rectangles, which we found to equal 2. Now we just need to do some rearranging on this. So we'll multiply by 16 ln 2. We'll use our log laws to put the coefficient onto the power of 2 inside the log. And we'll take e to the power of both sides of this inequality, which cancels out the ln. And we have e to the 15 is less than 2 to the 32, as required. Question 30. A continuous random variable x has cumulative distribution function given by this function, and part A, show that k equals 3. Notice here that we're given the cumulative distribution function, which essentially means that an integral has already been done on the probability density function. We know that the area under the curve, that the sum of the probabilities has to be equal to 1. Now, since this is the cumulative distribution function, this function here will give us the area under the curve, or the probabilities up to the value of x that we plug into it. And we can see that the domain of the probability density function is between 1 and e to the 3. On cumulative, before the beginning of the distribution, you have 0 probability. And at the end, you'll have all of the probabilities added up, and it'll stop there when it sums up to 1. So if we substitute in the ends of that domain, we know that this would have to equal to 1. So let's substitute in e to the 3 to this function here. And we know that would have to equal 1, again, since that's the end of that domain for the probability density function. And we can solve for k. ln of e to the 3 simplifies to 3, and so we get k is equal to 3. Now part B, given that the probability that x is less than c is equal to 2 times the probability that x is greater than c, find the exact value of c. So to find the probability that the random variable is less than a certain value of x, we would normally use the cumulative distribution function and just plug in that value of x. So the left-hand side of this equality is 1 over k, which we found to be 3, ln of x, in this case, we're going up to c. Now, to get the probability that the random variable is above a specific value of x, we can use 1 minus the value of the cumulative distribution function at that value of x, because that cumulative gives you the probability up to that point. And if you do 1 minus that, you'll get the probability after that point. So we'll do 1 minus 1 over k, which is 3, ln x, again in this case being c. And now we can solve for c. I'll simplify a little bit first. Let's add 2 ln c to both sides. And divide by 3. And raise both sides to the power of e. So c is equal to e squared. Question 31. A line passes through the point P, 1, 2, and meets the axes at x, which is x, 0, and y, which is 0, y, where x is greater than 1. Show that y equals 2x over x minus 1. Okay, what are some features of the graph that we could use here to set up an equation that might involve fractions? Something like the gradient could be helpful here. So we know that no matter what 2 points you pick on a line, the gradient has to be equal. So what if we set up the gradient from here to here and the gradient from here to here and set those equal to each other? Let's see. So for the first part, the rise is going down by 2 minus y. And it's going across by 1. For this second part, it's going down by 2 and across by x minus 1. We can set these two gradients equal to each other and see what happens. So I'll swap y to the other side and add this fraction onto the other side. Okay, let's get this to be all one fraction. And that's what we needed. Part B, find the minimum value of the area of the triangle XOY. So let's first set up the area of the triangle. 1/2 base times height You can see from the diagram that the base is x and the height is y. And we want to minimize it, which means we'll need a derivative. However, we have two variables. Now in part A, we found an expression for y in terms of x. That will allow us to replace y in the formula for the area in terms of x, which will allow us to then do a derivative and find a minimum. All right, let's do the derivative with respect to x. This will require the quotient rule. If you need to look, the quotient rule is on the reference sheet. That's this one here. V times the derivative of u minus u times the derivative of v, all over v squared. So we'll have x minus 1 times the derivative of x squared, which is 2x, minus x squared times the derivative of x minus 1, which is 1, all over x minus 1 squared. Let's simplify that a little bit. Now, minimums occur at stationary points, and stationary points occur when the derivative is equal to 0. Now, when you have a fraction equal to 0, the only way for that to be 0 is for the numerator to equal 0. So we'll solve x squared minus 2x equal to 0. We can do that by factorizing. So we'll have stationary points at x equals 0 and at x equals 2. Okay, just because we have a stationary point doesn't necessarily mean it's a minimum. Now there's only one we can consider here, so it's probably the one we're looking for, but we are supposed to show that this is a local minimum. So we could do the first derivative test or the second derivative test, but doing the second derivative on this function probably won't be very fun. So let's just do the first derivative test. Let's pick a value on each side of that stationary point of 2, but let's also remember that x has to be greater than 1. So we'll have to pick something between 1 and 2, perhaps 1.5. Now, 1.5 squared is 2.25. So the first derivative will equal 2.25 minus 2 times 1.5 over something that's squared. Really, we just care about what's the sign of the derivative. Now, I know the denominator has to be positive because it's squared, and the numerator is negative. A negative over a positive is a negative. So between 1 and 2, our function is decreasing. Now let's try a number to the right of 2, such as 3. When x is 3, the derivative will be 9 minus 6 over, again, a positive number. And 9 minus 6 is positive. A positive over a positive is a positive. And so we know our function is increasing after 2. This tells us that 2 is a minimum. So we verified that x equals 2 is where a minimum occurs. However, the question is asking for the minimum value of the area. So let's take that value of x and substitute it back into the expression for area that we have that's solely in terms of x. So the area will be 2 squared over 2 minus 1, which is 4 square units. And that is the minimum area of the triangle. Question 32. In a reducing balance loan, an amount P dollars is borrowed for a period of n months at an interest rate of 0.25% per month, compounded monthly. At the end of each month, a repayment of m dollars is made. After the nth repayment has been made, the amount owing a n dollars is given by, and then we have this formula. You've probably done work in the past to create an expression for an. In this case, they're going to have us do something with it, so they've already provided that to us. Now, part A. Jane borrows $200,000 in a reducing balance loan as described. The loan is to be repaid in 180 monthly repayments. Show that M is equal to 1,381.16 when rounded to the nearest cent. So, to find the monthly payment given the other parameters of a reducing balance loan, we need the expression for AN, and then we go to the end of the loan when we know it will be paid off. If the loan is to be repaid in 180 monthly payments, that means that when N is 180, AN, the amount left owing, will be 0. And that will allow us to solve for M. So AN 0 equals P, the principal, in this case 200,000, times 1.0025 to the power of N, which is 180, minus M times. Now, this part is a geometric series. This is the point in these kinds of questions where we want to re-express this using the formula for the sum of n terms of a geometric. That formula is on the reference sheet. So here we have the sum of n terms of a geometric series, and we usually use this version in reducing balance loans because r will be bigger than 1 point something. So let's use that to re-express that sum. It's A, the first term. The first term here is 1. R, the common ratio, 1.0025, as each term is that times the previous term. And of course, N will be 180. So it's going to be A times R, 1.0025 to the N, 180, minus 1 over R minus 1. We can clean that up a little bit. Now, what I'll usually do is I'll treat this as one negative term and add it to both sides. And the last thing to do to solve for M is to multiply by the 0.0025 and divide by the bracket. So we just have to calculate that. So we get M equals 1,381.16 as required. Part B. After 100 repayments of $1,381.16 have been made, the interest rate changes to 0.35% per month. At this stage, the amount owing to the nearest dollar is $100,032. Jane continues to make the same monthly repayments. For how many more months will Jane need to make full monthly repayments of $1,381.16? So what we'll do is we'll treat this as a new loan. We'll change the interest rate to 0.35%. We'll keep M as $1,381.16. And what we need to do is find N. And since we know how much is owing at this point, we'll know P is $100,032. So we were given this formula at the beginning for NEP, for M, and we know where the 0.0025 comes from, the interest rate, so we can modify this formula to suit our new situation. So we'd have AN equals P times 1.0035 to the power of N minus M times the sum of the geometric sequence. Now, for that geometric sequence, A will still be 1, R will now be 1.0035, and N is unknown. Let's put that all together, and we're going to solve for N. So once again, we're going to be looking at when this is paid off. That will give us the N number of repayments to get to 0. The principal is the amount left owing, which is $100,032. M, 1,381.16. And the sum is going to be 1 times 1.0035 to the power of N minus 1 over R minus 1. Once again, let's clean that up. I've written this part slightly differently so that the stuff that involves N is a little bit separated from the constant stuff, and I've just put the 1,381.16 over that denominator and then multiplied by that bracket on the right. Now I do that so that I can more easily expand that bracket. Okay, the next step will be to expand this bracket so that we don't have N inside a bracket anymore. Now careful here because this is a minus times a minus, and this will become plus. Next, we're going to factorize out the exponential with n in it. So instead of having two n's in the expression, that'll just be 1. And at the same time, I might move this term to the other side. Now what we're going to do is divide by that bracket, this one here. That will give us what 1.0035 to the power of n equals. At this point, we want to calculate it and see what it comes out to as a decimal. So we'll get 1.339569, some digits. We'll keep that in the calculator so we can use it in the next step. Let's bring that up here for a moment. So now what we'll do is we'll take a log of both sides, ln perhaps. We use a log, or we can put n in front of the log. And then we'd solve by dividing by ln of 1.0035. So on the calculator, I want to take ln of the answer divided by of 1.0035. Now it says, how many months will she make full payment? So 83 months of full payment, and then a partial payment. The 0.67 is part of a month's worth of payment. So we'll go n equals 83. And that seems reasonable since originally it was 180 months. She's made 100 payments. Normally it would have been 80 more months. The interest rate went up, so it takes her a little longer to pay it off. Part C, the final repayment will be less than $1,381.16. How much will she need to pay in the final repayment in order to pay off the loan? So, for 2 marks, I think what I would do is to find out how much has been repaid at A being 83. What is A at 83 on this new loan that we've created? So it's P minus M times the geometric sum. So let's work that out. So there's $928.29 left owing after the 83rd payment. Now, interest will be applied for 1 more month and then she'll make her payment. So we'll multiply that by 1.0035 to get $931.54. Okay, thanks for watching. I hope that helped you a little bit in your studies for the HSC. Make sure you like and subscribe. We'll be putting more content out with work solutions. Have fun studying.